For those of you enrolled in Physics AB, the center of mass calculation that we went through was just for a system of point masses arranged in 2 dimensions. For those of you in Honors Physics AB or in AP Physics C, you saw one or a couple of examples of how you set up an integral to find the position of the center of mass for a continuous distribution of matter. In theory, we should be able to set up such an integral for any type of an object in 3 dimensions. So for example, if we wanted to, we could probably set up some sort of triple integral, a three-dimensional integral to find the position of the center of mass of this tape assembly. Okay, that's all fine and good, but frankly, so what? In other words, what is the physical importance or significance of the center of mass? So what's important? About the center of mass. Okay, to answer this question, let's just write down, in terms of point masses, the equation that describes the position of the center of mass. So recall from the previous lecture, that's the following. First of all, we have the product of each mass with its position vector, and then we add it all together, and then we divide by the sum of the masses. Let's say that I have a system of masses in some manner. I'm going to use this weird-looking green hose here, like so, as my system. Let's immediately simplify the denominator of the expression behind me. The denominator of the expression behind me is nothing more than the total mass of this green hose. So let's just write the total mass of the green hose here, the denominator of the expression, as M. Like so. Okay, now in order to be able to describe the physical significance of the position of the center of mass, at this point what I'm going to start to do is I'm going to take derivatives. Now if you go back, of course, to basic kinematics, for example, right here we have a position vector. If you differentiate position with respect to time, this then gives you velocity. So without going through the details of actually calculating a derivative, let's just say that if we have position as a function of time, we differentiate it, we then end up with velocity as a function of time. So let me go ahead, first of all, and erase this right here. And now let me just write in words, take a derivative with respect to time. Okay, so when I do that, we go from position to velocity. So then therefore, the velocity of the center of mass is then therefore equal to the following expression. Right here is the position for one of the particles that makes up the system, the green hose. So then therefore, if you differentiate position with respect to time, you end up with the velocity of that particle. Once again, that makes up the green hose. Okay, now this is a velocity equation. In just a few moments, I'm going to take another derivative. And then when you take derivative of velocity with respect to time, that then gives you acceleration. Before I do, however, I'm going to do an extra step off to the side. What I'm going to do is take the total mass of the green hose and move it over here to the left-hand side of the expression, such that I end up with the following. This expression here. And now we have a new quantity, mass times velocity. This new quantity is referred to as momentum. Momentum is always denoted as the letter P. It is a vector quantity, and it's equal to mass times velocity. Now, it is a new quantity for us, so let's just go ahead and check the units. And when it comes to the units, the only thing that we have to worry about is the metric SI system. So you have mass in kilograms multiplied by velocity in terms of meters per second. And we just leave it like that, kilograms, meters per second. We don't give it its own name or its own symbol or anything like that. Now, exactly what is meant by momentum? Well, here's how Isaac Newton himself referred to it in Principia back in the 17th century. He thought of momentum as a description of the total quantity of motion associated with a system. The total quantity of motion of a system depends upon 2 things: the velocity of the system, but also its inertial mass. So then therefore think of this quantity, mass times velocity, as a measurement, if you will, of the total motion of a system. Measurement of the total motion system. The total quantity of motion, as Newton himself originally referred to it as. So then therefore, in terms of this new quantity, momentum, right here on the left-hand side of the expression is the momentum of the center of mass of the system. That's really what it is. And then on the right-hand side of the expression, we have the sum of the momenta, as we say in plural, the sum of the momenta of all of the individual particles, for example, that make up the green hose. Like so. Okay, now we're going to put this off to the side for now. I'm going to leave it here on the board. We're going to put this off to the side for now and then come back to it again in just a few minutes. And now let's go back to here. Once again, we started with the position equation. We took a derivative and we ended up with a description of a velocity. That then gave us this new quantity, momentum. Now I'm going to go another step. Let's go ahead and take another derivative with respect to time. And when we do, recall that the derivative of velocity is acceleration. Okay, so here on the lower board, take another derivative. With respect to time. So then therefore the derivative of the velocity of the center of mass is now the acceleration of the center of mass. And then on the right-hand side of the expression, right here we differentiate the velocity of the ith particle with respect to time. That then gives us the acceleration of the ith particle with respect to time. Notice the mass times acceleration that we begin to see here once we've taken these two derivatives. Specifically, let's take the mass of the system now and move it here to the left. Like so. And then I get to this step here, and let's now interpret it. Okay, first of all, recognize from Newton's second law, mass times acceleration is net force. So then therefore, this right here is the net force exerted upon the center of mass. And then take a look at the right-hand side. Just take a look at the m sub I times a sub I. This right here is the net force on one of the particles that makes up the system. And then we add up all of those forces. In other words, the right-hand side of the expression is equal to the sum total of all of the forces that are acting on all of the particles that make up this system. Okay, now what can we say about those forces? They actually fall into two broad categories. Before I describe those categories, however, let me just write the following for the right-hand side of the expression. This is just the sum total of all of the forces that act upon all of the particles that make up the system. Take a moment to pause if necessary and write down this description. Okay, now what can we say about those forces? What can we say about all the forces that act on all the particles that make up this green hose? Well, as I said a few moments ago, those forces fall into two broad categories. There are, first of all, internal forces, the forces that occur between all the molecules and all the atoms and blah, blah, blah that make up this object. And then secondly, applied to the system as a whole, we have what are referred to as external forces, such as, for example, the external force of gravity, which is applied to all portions of the green hose equally. So then therefore, the sum total of all the forces that act on all of the particles is the addition of those two categories of forces, the internal forces and the external forces. There's a specific way of writing this. We write that in the following way. Okay, first of all, we have the net force exerted upon the center of mass, the left-hand side of the expression. And now I'm going to rewrite the right-hand side of the expression as the addition of the internal forces that occur between all of the atoms and molecules and blah, blah, blah that make up the green hose, and any external forces, such as gravity, that are applied to the system as a whole. Once again, as I said, there's a specific way of writing this. Like so. Go ahead and copy that down. Let me explain the notation. Okay, first of all, this right here is just the sum of the external forces acting on the system as a whole. Gravity, for example, would be a nice illustration of that. And then we've got this notation right here, this weird summation symbol that's describing the internal forces that occur between all the atoms and molecules that make up the green hose. Here's what this expression says, but let me simplify it for you. Okay, now instead of considering the system to be that weird looking green hose, instead consider the system to be these two objects like so. Object number one and object number two. If I bring them together like this, they then exert internal forces upon each other. And now here's how you read this expression. We have, first of all, the force on one due to two, the force on one due to two, plus the force on 2 due to 1, so plus the force on 2 due to 1, but not the force of 1 onto 1, and not the force on 2 due to 2. In other words, each object only exerts a force on the other. Each object does not exert a force on itself. So it's basically the force on 1 due to 2 plus the force on 2 due to 1. What could you say about the sum of those two forces and why? It's equal to 0. It's equal to 0 by Newton's third law. It's an equal and opposite reaction pair. Recall that if I bring two objects together like so, the force on 2 due to 1 points in that direction. That's the action. The reaction, however, is the force back on 1 due to 2 in the opposite direction, equal in magnitude, but in the opposite direction. Therefore, if you mathematically add the two together, you end up with 0. So in other words, all of the internal forces acting on the system, it all cancels out by Newton's third law. 0 by Newton's third law. Okay, and now look at what is left. This expression here. And now here's what this expression says. This is the importance of the center of mass. Any external forces applied to the system as a whole mathematically behaves as if it's only applied to one location, the center of mass. So any external force applied to the system as a whole mathematically behaves as if it's only applied to the center of mass. So let me illustrate this for you in a couple of simple demonstrations. In order to do so, I'm going to take my camera and I'm going to move it back to the next row. Give myself some room here. Allow me a moment to do this nicely and carefully. All right, so I'm very carefully moving my camera backwards to the second row. Like so. Let me tilt the camera as well, like so. And now consider, for example, a projectile, say my eraser. Of course, in our unit on kinematics, we studied projectile motion. And what is the path that is traced out by a projectile? It's a parabola. But specifically, what about the object is tracing out a parabola? It's the center of mass. Because the external force of gravity applied to the eraser as a whole, it mathematically behaves as if it's only applied to one location, and that's the center of mass. So then therefore, if I take the object, for example, and I do something like this, the center of mass of the eraser traces out a perfect parabola. You also saw the eraser rotating. The rotation is about the center of mass because the center of mass itself traces out a perfect parabola. That's not just the case with my eraser, but also with my strange-looking green hose. So here's my weird-looking green hose once again. Okay, the green hose is not uniform. There's a little bit of extra mass right over here because there's some duct tape here. So then therefore, the center of mass of this thing is not in the geometric center. It's maybe closer like so to the weird-looking green hose's duct tape like this. It's this point right here then that traces out a perfect parabola when I toss the object in space like so as a projectile. And any rotation that you see is then therefore about the center of mass. Same thing if I make the situation a little bit more complicated. Let me go ahead and take this right here and then stick it in there like so. And now when I take this object and toss it, as you'll see, it behaves a little bit strangely. It appears to wobble in a weird way, for example, when I do this. But the whole time, the center of mass of that more complicated system is tracing out a perfect parabola, and any rotation that you see is about that point. It doesn't matter if the little object inside the hose is sliding around inside the hose, because any force that it exerts upon the hose is exactly canceled out by its equal and opposite reaction pair from Newton's third law. All of the internal forces cancel, they don't matter. The only thing that does matter is the external force of gravity. Okay, now what does any of this have to do at all with this new quantity called momentum? Okay, now I know that my camera is back in the second row, but hopefully you'll still be able to see this. Let me go ahead and do some erasing here. Okay, so now let's ask and answer the following question. What happens if the sum of the external forces, is equal to 0? So the mathematical sum, the vector sum of those forces is 0, or there are no external forces to begin with. Let's just think of it like that to keep it simple and straightforward. So for example, let's say I take this green hose again. I'm going to take the object out of it. Let's say I take this green hose and I'm in outer space somewhere. So there's no planets nearby, no stars, no nothing. So there's no gravity. And then I take the object and I throw it. What happens? Well, if the sum of the external forces is equal to 0, then the acceleration of the center of mass is equal to 0. Therefore, this quantity is equal to 0. But recall that acceleration is the derivative of velocity. Therefore, this quantity is constant. And this quantity here is this new quantity called momentum. In other words, the momentum of the center of mass, which is the sum of the momenta of the individual particles that make up the object, is a constant. It's a conserved quantity. This is referred to as conservation of linear momentum. In Isaac Newton's terms, the total quantity of motion doesn't change. It's a conserved quantity. Now, in the case of this green hose, if I am out in outer space somewhere, and then therefore the sum of the external forces is equal to 0, and I throw this thing, what then happens? Well, this point right here, the center of mass, well, it has a constant velocity. So it obeys the law of inertia. This point right here moves in a straight line at a constant speed. And then any rotation that you see is a rotation about that point. In other words, the total quantity of motion of this system is a conserved quantity. The momentum of this system is a conserved quantity. Now here's a slightly more complicated situation. I'm going to set this up as a demonstration. My demonstration is going to involve a skateboard. What I have to do, however, is I have to once again tilt my camera. So bear with me as I do this. All right, so tilting the camera like so in this direction. Okay, now right here is a skateboard, like so, which I'm going to place onto the floor like this. I'm going to use the skateboard here to mimic a horizontal frictionless surface. So then therefore, if I stand on the skateboard, watch this. Okay, first of all, external force, and now I get on the skateboard like so, and I stand here. If I use the skateboard as a means of mimicking a horizontal frictionless surface, this then means that the sum of the forces, the external forces acting on me and the skateboard as a whole, is 0. There's no force horizontally, and the normal force upwards is canceled out by the weight of the system downwards. Therefore, right now, the sum of the external forces is equal to 0. This then means that the acceleration of my center of mass is equal to 0. Therefore, the velocity of my center of mass is a constant. Now, I'm just standing here to begin with. So right now, the velocity of my center of mass, and my center of mass, by the way, is roughly in the center of my body. The velocity of my center of mass right now is equal to 0. And it's equal to 0 the whole time, for example, when I say do something like this. Shift back and forth on the skateboard. Because when I shift back and forth on the skateboard, any force that I exert upon the skateboard is an internal force, which is exactly canceled out by the equal and opposite reaction pair. Once again, the only thing that matters are the external forces. So if the sum of the external forces is equal to 0, the acceleration of my center of mass is equal to 0, therefore the velocity of my center of mass is a constant. But it's equal to 0 to begin with, so then therefore it's equal to 0 the whole time as I shift back and forth. This means that relative to the floor, the position of my center of mass never changes. However, if you watch me do this over the course of a couple of iterations, you probably have begun to notice that I've started to drift a little bit in that direction. And the reason for that is perhaps twofold. Number one, the floor itself may not be completely horizontal. It may be tilted slightly in that direction, so there would be an external force of gravity in that direction for that reason. And in addition to that, of course, there's a little bit of friction between the skateboard and the floor below. But if the floor was perfectly horizontal, and if it was a perfectly frictionless surface, then the position of my center of mass relative to the ground would never move. Now, normally I demonstrate this situation with two people, myself and a student. We are then both standing on skateboards and we are connected to each other by means of a pole. And then we shift back and forth on the skateboards, much like I'm doing here on this single skateboard. And then in that demonstration, what you see is the position of the center of mass of that system relative to the ground never moves. That's then what I turn into the first quantitative example. I'll do that example after we conclude this video. So let me go ahead now and get off the skateboard here carefully. By the way, just only a couple of months past knee surgery. So I'm going to use external forces like so to safely get off the skateboard.